Hello, everyone. Come on in. Computer's a little slow getting online again. Hope nobody's scared for my sitting. I was just letting you know that be careful when you came out of the bathroom.
Okay.
I'm in class now, baby. Anybody have any questions while we're waiting for other people to get started?
Yeah, Professor, when's our midterm going to be? I saw on the syllabus it was October 23rd-ish.
It's actually, I think October either 19th or 20th is what I ultimately put on the syllabus. I just wanted to show you that artwork I bought yesterday. That's the artwork. It's mass manufactured, but I still like it. Yeah, I just checked yesterday and I put it in my calendar. In fact, let me double check here. You guys meet on Tuesday and Thursday. So yours is supposed to be on, yes, yours is supposed to be on the 20th. So what we'll do is that day, you would just come into, you don't have to come to this Zoom meeting or anything, but there will be a online version of the practice, of the final, midterm, that'll have respondents on it. And I'll actually make it up the week before a practice one that has respondents on it that you're supposed to only take exactly once, meaning you take the practice respondents midterm once, just enough to get through the beginning instructions and make sure everything works and make sure it updates the software in case you already have it installed. And you can answer the questions if you want, but it really doesn't matter. That one's not ever going to count as a grade. But then there'll be another one that doesn't have respondents, and you take that repeatedly to practice for your midterm. So the midterm will be on October 20th, that whole week. So starting basically that Monday. Actually, I'll probably start a little earlier. I'll probably put the midterm practice exam, both of them, up at least 7 days before the 20th. So that'll be like the 13th. I might even put it a little earlier, but definitely by the 13th. So you can take that. What you need to do is as soon as that respondus midterm practice comes up, you need to take that immediately. And I'm telling you this very, very seriously right now, because every semester I have someone that don't do it. They say, I haven't used responders, I don't need to do that. No, you do need to do that, because I've had students that basically ended up not being able to take it at the time they're supposed to take it, which made me have to make another one. So if you miss that opportunity, I'm going to dock you points, because I just can't do all that extra work just because one student refused to listen to me. So make sure, as soon as I put that respondus practice test up that same day or the next day period, make sure you take that respondus. Again, you don't have to take the actual quizzes. You just got to get through the whole process where it allows you to start. If you want to take it, it's fine. It'll grade it and everything. And that's not going to count against you or for you as far as a grade goes, but I'll see at least that you did that. At that point, your browser and your computer will have the proper respondus software on it so that you can run the actual midterm. We often do this for online classes. We just have you do it in the lab. I don't think that necessarily works very well for your lab instructor. If that's the case, then we're, as I've just finished saying, we're going to do it by respondus browser. If I can get it to where it's a face-to-face test, then you can do it in your actual lab time, but I have to work with your instructor to find out that for sure. I would prefer to do it face-to-face. It will be multiple choice. It will probably be on Canvas, and you'll have a lockdown browser being used even there in the lab. So ideally that would be the ideal scenario, but I don't know if she can afford the missed lab time. So I'll find out for sure. You had Miss Reskovic, right? For lab? Or do you have?
Yes, that is correct. Yeah.
Okay.
Correct.
Gotcha. I'll double check with her, but I know she said she was going to cancel some lab. I think that was today, in fact.
Yes, tonight.
Yep, it's tonight.
Okay, I'll just make sure with her. But like I said, you might even be able to do that with them, in which case you can just take it with your own computer just in case, but you're probably gonna you'll probably be doing it in the lab in real time. That way you can just use your Spondus lockdown browser and not the whole video camera thing. That would be sufficient. Okay. All right, so we cleared all that up. Anybody have any other questions about material or whatnot? Okay, so last time we were talking about Kirchoff's laws. That's basically the last thing I went over. In Kirchoff's law, the Kirchoff loop rule is really just a conservation of energy concept. Remember, potential energy is an energy type and it's measured in joules, whereas the voltage, the electric potential is another name for it, is the electric potential energy per unit charge. So volts are actually joules per coulomb. So it is really, when you talk about the increases and decreases of voltage going around any closed loop, they add up to give you zero. That's just saying, hey, energy is conserved. The Kirchoff's junction rule means all the currents coming into a junction add up, and all the currents going out of the junction add up, and those two sums got to be equal to each other. And that's a conservation of charge problem. So tonight I want to make sure I use that a couple times, and I'm going to solve a multi-current circuit, and we're going to use that, show you at least a way of solving that system of equations. It'll be 3 equations and 3 unknowns. And then I'll do a couple other circuits. I'll do charging a capacitor and discharging a capacitor, and I'll make a galvanometer into an ammeter, and a galvanometer into a voltmeter too. So that's what's going to happen tonight. Let's go ahead and see if I can share my screen. Oh, got another person to come in. All right. So those of you coming in just now to class, make sure when this video goes up tonight, and I think I've already put your other one up from last. Yeah, I definitely put your one up from last week. Make sure you watch at least the beginning of this, the first, I guess we're looking at maybe 7 minutes of it. So you'll hear what I just announced about the midterm. So let's see if I can share screen now. Do that. Do this. See if it works. I am not yet seeing an option for, there it is. Yes, it worked. Okay, so what I went ahead and did is I went ahead and drew the first circuit, and this is very much like the one in the book, the very first one they do in the book. So I didn't want to deviate too much from that, but I did put up 3, I think, videos links in this week's module where I've solved other circuits. So you can see that as well. Another person just came in. So I'm going to solve this now using Kirchoff's loop rules and Kirchoff's junction rule. And from that, you'll see more or less how this process goes. Now, you got to remember the rule with the Kirchoff loop rule is if you go across a battery from short arm to leg arm, like you see on the 45-volt battery right there, if I go across that from right to left, I'm going from the little short side to the high side. So that's a voltage increase. If I now continue going to the left along that one wire, then I'll go through that 1 ohm resistor, and I'm going in the direction of current I3. Y'all see the red arrow? That tells me which way I3 is going. I made that up. It happens to be the same way your book did, but be advised, we don't have to give you those directions at all. You have to make those up in general. Okay. So if I go across a resistor in the direction of current, that is a voltage drop. But if I had went the other way through that 1 ohm resistor, that would be considered a 1 ohm times I3 voltage increase. And if I continue to go through the right, going from the big side of the 45-volt battery to the small side, that would have been a voltage decrease. So that's the key to using this. So what I'm going to do right now is I'm going to start from this dot right here that I just drew. Let's make it in red. Okay, I'm going to start there, and I'm going to go counterclockwise all the way around the top loop. Actually, before I do that, let me use Kirchoff's junction rule. So let me say Kirchoff's junction rule. Okay, that's going to give me, notice that current I3 goes into this junction right here. I2 and I1 come out of it. So I can say, here's equation 1, I3 is equal to I1 plus I2. So that's how you deal with Kirchoff's junction rule, is you just find the one that's one or so that's going into it. And that those are added together and put on one side, and then find the 1, 2, or 3 or whatever that's leaving it. And those are added up on the other side to equal instead of equal. Now I'm going to go counterclockwise from that first circle I drew, the one right by the S in solution and solve. So notice I go plus 45 volts. So that'll be plus 45. I'm leaving the units off to make it easy. Okay. And then I'm going the direction of the current through R1. So that'll be a I times 1, or a 1I drop. And then I go I3 times 40 for another drop. So 40 and 1 gives me 41. So I'll go minus 41 I3. Okay, so that accounts for the 1 ohm and the 40 ohm. Next, I'm going with the direction of current I1, and I'm going across the 30 ohm resistor. And I'm going, since I'm going that direction, that's a voltage drop. So that'll be minus 30 I1. And now I'm back to the dot I started at. So I'm going to write that as equal to 0. This is going to be equation 2. Okay. And then I am going to let's do the bottom loop this time. So I'm doing it different from the way your book did. I think your book did the upper loop and then it did the outer loop. And that way works fine too. And you get a different set, or at least one different equation, and a slightly different way to solve it, but it's still okay. And I think the more ways you see, the better. So that's why I'm choosing to do it a different way than the book did. So I'm going to now go, in fact, clockwise from the same dot I did, but around the bottom loop. So I'm still starting at circled junction next to the S in solution, but I'm going to go clockwise. Notice by doing that, I am going against current I2. And that's exactly why I'm doing it, because I want you to see what you have to do in such a situation. So first I go through that 20 ohm resistor and I'm going in a downward direction. So that's opposite of I2. So I'm going to say that's plus 20. Actually, let me hold a second. I'm going to go plus 20 I2, and then I'm going to go plus 1 I2. So I might as well say plus 21 I2. That's why I stopped and redid it. So I can go ahead and get both of those resistances at the same time. Now I'm going from the long bar of the battery to the short bar. So that means the 80 volts is a voltage drop. So I'll say minus 80, like that. Now I get up to the next red junction and I'm going to take a right. Again, I'm going against the current. I'm going in the opposite way of I3, and I'm going to go through a 40 ohm and a 1 ohm resistor. So I'm going to say minus 40, or excuse me, plus 41 I3. Okay. And now I'm going again through the battery from the long side to the short side. So that'll be a minus 45 volts there. And I'm back to where I started. So I call that equal to 0. Okay. So now I've got 3 unknowns, I1, I2, and I3. I've got 3 equations. They're not easy multiples of one another. That's what happened. For instance, if you trace the same loop again, but went in the opposite direction, that would just be off by a negative. So I wanted to go ahead and show you that even with this craziness, we can, by going, against the direction of the current, we can still get the right answers. So let me show you how that's going to play out. First, I'm going to take equation 2 and solve for I1. So solve 2 for I1. So what I'm going to get is I will get, when the I3 term comes to the other side, that'll be positive. So I'm going to say 45 or 41 I3 minus 45 over 30 is equal to I1. Okay. And I can even make that easier by keeping an extra sig fig. Notice everything's only to one actually 0 decimal places are 1 sig fig. When I added the 40 and the 1, that was allowing me to keep 2 sig figs. So now I'm going to divide 41 by 30. And that's going to give me 1.37, carrying an extra digit. So that's 1.37 minus I3, excuse me, minus 45 divided by 3. That should be basically 3 over 2 or 1.5. So I can call that minus 1.50. So we've got that one. That's now an expression I'm going to call equation 4. So let's call this equation 4. Okay. Now I'm going to solve equation 3. For I2. Okay. So in this case, I'm going to get I2 is equal to, notice if I pull all that other stuff to the other side, one thing I can do is I can go ahead and combine the negative 80 and the negative 145 to get negative 125. But when it goes to the other side, it's going to become positive 125. So I'm going to say 125. Now the negative 41 or the positive 41 I3 on the left is going to become negative 41 I3 on the right. So I'm going to say minus 41 I3. And now I've gotten everything but the 21 I2 term to the right-hand side. Now I'm going to divide both sides by the 21 like that. And again, I can interpret this using 3 sig figs just to make sure I'm covering all the bases. 125 divided by 21 is going to give me 5.95. And since that's division, that's really still only 2 sig figs. So then I'm going to have minus 41 divided by 21. And that's going to give you 1.95. And that's times I3. So now I have equation 5. Which is a expression for I2 in terms of I3. 4 is an expression for I1 in terms of I3. And we can look at our trail and see that I've used equation 2 and I've used equation 3. You've got to make sure you use all 3 equations when you have 3 unknowns. If you have more equations, you got to make sure all of them work, and you're more likely to find a contradiction that just is unsolvable. When you have more unknowns and or more equations than you have unknowns, that can actually create a problem where you can't get a solution at all. If you have 2, in fact, there might, in fact, when I say you can't get a solution at all, meaning none exists. Okay. However, if you have like 2 equations and 3 unknowns, that one's just impossible to solve. It's not defined well enough. Okay. So in this case, I know I've used equation 2 and 3, so I clearly still need to use 1. And that's part of what I was seeing when I decided to solve 2 for I1 and 3 for I2, because I can substitute my value of I1 from equation 4 into equation 1. I can substitute my value of I2 from equation 5 into equation 1. And then I'll have I3 on is the only unknown in equation 1. So let's plug 4 and 5 into, that's the worst looking 5 I've ever written, 4 and 5 into 1. So when I get that, notice the left-hand side is just going to be I3. So I'm going to say I3 is equal to 1.37 I3 minus 1.50. And then notice the symbol between the I1 plus I2 is just a plus. If that was a minus, you'd have to remember to distribute that minus throughout the whole equation 5. But luckily it's a plus, so I can just write this down as is. I want to say plus 5.95, again, marking my extra sig fig, minus 1.95 I3. Okay, so you see now all the unknowns.
How did you get
Go ahead.
1.37i minus 1.5 for equation 4? Shouldn't
So
those
41
be
divided by
negative?
30. Yeah, 41 divided by 30 should be 1.37.
Right, that should be negative 1.37, shouldn't it? If you take equation 2 and you were to add 30i1 to both sides, once you get 45 minus 41i3.
Yeah, it's got you. So yeah, I ended up flipping signs. Nice catch. So yeah, I was trying to solve 2 for 1. Yes. So if I pull the negative 30i1 to the right, then that'd be positive, and then it'll be 45 minus 41. So let's make that correction right now. Thanks for catching that. Was it Matt?
Nate,
Nate. Okay, thanks, bud. So what I'm going to do is I'm going to put a minus in front of this, and well, actually, no, I can't use that color. I'm going to put a minus here and a plus there. Okay, that fixes it there and there, and that fixes it here and here. Okay, I had a sign error. Let's double check, make sure I didn't make a sign error in making up equation 5. Equation 5 came from equation 3, and I was solving for I2. That one was already on the left and positive. So that should have been 41 should have came to the other side and been negative, and 80 and 125 should have came to the other side and been positive. So that one looks okay. So I'll put this one's okay. All right, now that we got that, and now I'll fix this, we can go ahead and deal with our I3s. It looks like I'm going to have a 1.37. If I keep all the I3s on the right, I'm going to have 1.37 negative plus 1.95 negative. So that's going to give me a net negative on the right hand side. And then what I'm going to do is add, excuse me, I should actually put them all to the left hand side. Yeah, let's pull them all to the left hand side. I like that better. So I'm going to pull all the I3s to the left hand side. That's going to give me 1 plus 1.37 plus 1.95. So 1 plus 1.37, 1.95 gives me 4.32. So now I have actually, let me not write it in that color. Now I have 4.32 I3 on the left-hand side is equal to, now I'm going to take the 1.5, which is positive, and subtract from it negative 1.95. So I get negative 0.45. Everybody see that?
I thought it was 7.45.
Oh, there's a 5 in there. Yeah, exactly. I ended up adding the 2 wrong numbers. I added 1.95, which is an I3 term, and the 1.5. Thanks. Nice catch on that one too. Good gosh. What was I thinking? Okay, so let me get rid of this completely. Now, what I've done, I'll go ahead and mark this to keep me from making a mistake. And this also tells you one of the things, people like us do when we're solving problems, keep from making boo-boos. Which I obviously should have been doing. So we've already taken care of this term and this term and this term. So that tells me not to count them. But now you see all I have left is the 1.50 plus the 5.95. So that's 6.95, 6.45. Is that what you got?
I got 7.4.
Yeah, thank you. Okay, so now 7.45 is the answer here. And that was good because it was going to make me have only one sig fig, and I did not like that. So that means that I3 will actually be positive. And if I had chosen the wrong direction for I3, this answer would come out negative. but anywhere else I plugged it in, I'd still have to use the negative because that's the way the equations are set up. So that's just a caveat, a rule that you need to think about. So now I'm going to take the 7.45 and I'm going to divide that by 4.32. And I'm going to keep one extra digit and underline it so everybody knows. So that's going to be 1.72 amps. Okay. And that is the current I3. So we got that direction correct. And we now know the magnitude of it, of course, is 1.72 amps. Whole amps is what's typical when you're using single ohm resistors. If you're using kilo ohms or mega ohms, it's much more likely to get milliamps. So that's something ballpark figure to keep in mind. Now that I have I3, I can plug that in for my value of I1, because remember I1 was solved for in terms of only I3. So now I'm going to say this is number 6. I'm going to plug 6 into 4. Okay. And this is going to give me, in fact, I1 is going to equal 1.37 times 1.72. And then that's the negative we were supposed to use. So let me put that negative sign in there before I make another careless mistake. And then let me use the positive sign that I changed to. And then I'm going to add to that 1.50. And that should give me my answer. So 1.5 minus 1.37 times 1.72. And that gives me negative 0.856 amps. So evidently we got I1 as the wrong direction. What I'm going to say is, let's double check something. When I do 1.37 times 1.72, okay, what I get is 2 3 sig fig numbers. So that should give me to the second decimal place. And then I add with something that only has 1 decimal place. So really, I'm actually carrying 2 extra sig figs on here. I hate that, but that's what happens when you end up subtracting numbers. So technically, if we're being, I don't know, uptight about this, then we should only call that 0.9 amps or negative 0.9 amps. I'm not going to go that far. I'm just going to say I1 is equal to negative 0.86 amps. And that actually is still carrying 1 extra sig fig. And I really hate how bad that looks. I'm going to write it over again because I got OCD. Okay. So I've now got the second solution. And then finally, I need I3. So I'm going to plug 5 or 6 into 4 or into 5. Okay, so that says I2 will be equal to 5.95, 1 extra sig fig, minus 1.95, again, 1 extra sig fig, times 1.72. And that's going to give me 5.95 minus 1.95 times 1.72. And I'm not using any parentheses because your calculator should know the order of operations. And this becomes 2.596, which is way more digits than we want. But as you can tell, when I multiply 1.95 times 1.72, that gives me 3.354. So really, I should have 2 sig figs on that. And actually, I'm only allowed to have, therefore, 1 sig fig. So these 2 digits right here are extra. So I'm ultimately going to say that I2 is equal to 2.60 amps. and I've underlined what digit is not supposed to be included. And that's it. Okay. So that is a solution to a 3 current circuit, and one of many ways you can do it. Of course, these equations come out linear. You can see in equations 1, 2, and 3, you could have made equation 1 into 1I1 plus 1I2 minus 1I3 equals 0. That's a linear equation. Number 2 and number 3 are already linear, so you actually can use your matrix methods. If you get in a bind and you got 3, 4, 5, 6 currents, you can always go back and use a matrix method. There's also a method that you'll learn, at least I learned it in my engineering electronics course, called the nodal method. And there's another way called the I think it's the, I can't remember what it's called, something like the passing current method or some weird stuff like that. But the nodal method's really easy. What you do is you'd say the wire that goes from that red circle to that red dot right through the middle, that's one node. So we'd pretend the voltage at, say, that circle next to the S, that red circle next to the S, we'd put a little bubble there and say that voltage is 0 volts. We're allowed to call 0 anywhere we want, so that'd be fine. And then we'd say the other end of that I3 wire is voltage V. So we'd say, okay, well, I'm thinking the current's going up, so I'm going to say V plus 40I3 plus 1I3 minus 45 equals 0. That's the equation for that middle wire. For that other wire, it's V minus 30I1 equals 0. And for the bottom one, it's V plus 80 minus 21I2 equals 0. And with that, you automatically have each equation having a voltage, at least one voltage you don't know, and a current. So you can always solve for a single current, and then you just use Kirchoff's junction rule to relate the currents. You're automatically solved for one current in each case. You put them all in, and basically what you get is a voltage. So you have that voltage, and then you put that back in the equation. And that really takes a lot of the work out of it. So you'll see one of the videos I linked to is a nodal method. Feel free to check that out. It's pretty straightforward. I explained it right there. Also, a couple of you came in late, even after I made my late student announcement. So I just wanted to tell y'all to go back once this is posted and watch the first 7 to 10 minutes or so over where y'all have missed, because I mentioned stuff about the midterm and I don't want you guys to miss that. Okay. All right. So that's our first problem. Does anybody have any questions on anything we did? And thanks again, Nathan, for catching that sign error, because that would have been bad. And I hate it when it's bad. This does, in fact, give me the same answers that the book got for the similar circuit. Actually, I shouldn't say similar. It's exactly the same thing, except maybe I drew it in blue. Okay, so this does match their solutions as well. I think they had negative 0.87. I had negative 0.86, but he was rounding everything to the exact number of sig figs at each step, and that's the way Giancoli does a lot of his problems. So that's the difference between getting negative 0.87 and negative 0.86. So no questions? All right, now we have another. Okay, so this is a RC circuit, and RC circuit, other than what you're used to in RC cars, that means remote control, but in our case it means resistor capacitor circuit. Okay, this is a series setup, and what will happen if I throw that switch? Everybody sees the little switch that I have there. So if I close that switch, meaning it makes a complete circuit, what's going to happen is the electrons are going to flee from the negative. So I'm telling you what really is happening as opposed to conventional current. The electrons, which are negative, are going to flee from that little negative terminal of the battery. They're going to actually run through the resistance R and start to stack up on the top plate of that capacitor. And slowly the top plate of that capacitor will get more and more negatively charged. And each one of those negative charges is going to compel a negative charge in that bottom plate to run away. That bottom plate positive or negative charge is going to run through the closed switch and find out that, oh, it was attracted to, in fact, the positive plate. So little negative charge is going to be coming in the positive plate too, until we ultimately get that the charge on the top plate is the negative of the charge on the bottom plate. And that charge can be given by the capacitance C times E1, the electromotive force, or E, I think I wrote there, the electromotive force. Okay. By doing that, we'll know it's reached equilibrium, current will stop flowing, but initially current will flow as if there's no capacitor at all. So you initially get like a current, from Ohm's law, V equals IR, you should get I is equal to, I is equal to E over R initially, but it's going to fall to 0 after some time. And at that point, what's going to happen is the charge on the capacitor will be equal to C times V, C times E, I should say. And the voltage across that, of course, will be the same thing as C times V, or excuse me, the same thing as what you get when you divide the charge by voltage. So that's the real deal. What we're going to see now is that we're going to have in this position, we're actually going to have a Kirchoff's loop rule is one way of thinking about it. You have an electric potential E that's established, and then you can imagine the positive charges, for instance, flowing around, and that's going to sustain a charge on the capacitor that's going to change in time, and then that's going to create a current that makes a drop in voltage across the resistor. So the ultimate equation is going to be in terms of R and E and I and C. So what you ultimately have is E, actually I should write that in red. So what we have is E is equal to I times R plus 1 over C times Q. What we've used there is V equals IR, Ohm's law, and C equals Q over V, which is a definition of capacitance. So obviously,
Why did we switch to an E instead of just using the V?
Because we're going to have a lot of V's in here from the voltage as a function of time, and E is supposed to be the electromotive force of the battery. And then the R will include not only the resistance of the resistor, but the resistance of the wire and the resistance, internal resistance of the battery. But mostly it's just because they wanted another symbol other than V, because we're going to have a V that happens initially across, say, the capacitor. We're going to have a V across the resistor. And at least this way you can use that as a idea of this is what the voltage of the battery is. So, and it's for EMF. So a lot of times we just use E for a voltage anyways, just because electromotive force is what we used to call voltage. So yeah, it's kind of a weird thing, but it's not as hard to deal with as you might think. Now, what we can also do is we can realize that as this charge gets higher and higher on the capacitor, that's actually a result of the current getting higher and higher. And in fact, I is actually equal to dq dt. So I can now say that E is equal to R dq dt plus 1 over C Q. And I can make that a little easier or a little different just because I know where I want to go. So what I'm going to do is multiply or divide both sides by R. So that's going to be E over R is equal to dq over dt plus 1 over R, that cancels that out. So it's be 1 over RC times Q. Okay. Now what I can do is I can get the Q term on the left with the E over R term. So I'm going to say E over R minus Q, or minus 1 over RC times Q is equal to dq over dt. Now it really looks smart of us to go ahead and get a common denominator, in which case I can say that I will have C E minus Q over RC is equal to dq over dt. And now I've got it in a really nice separable form. So let me separate it. What I'm going to say is I have dq over CE minus Q is equal to dt over RC. So you can sort of think of that as like cross multiplying. I multiplied RC times dq, and then I divided both sides by dq, and then I flipped both sides over. So that's how I got that. That's another way of thinking about it. Now I'm going to take this and I'm going to integrate the left-hand side from q equals 0 to q of t. Q is a function of t. And this side, I'm going to integrate from t equals 0 to t. So that's going to give me, notice you can do a substitution. You can let u equal CE minus Q. So let u equal CE minus Q, then du is equal to minus dq. Whoa, that really looked bad. Okay, so all I need is a negative. I'm going to throw it on the other side. And what I'll get is the ln of, because the integral of du over u is just ln. So I'm going to get the ln of CE minus Q evaluated at Q equals 0 and Q of t is equal to, and remember that negative I had to throw in both sides so I could get the du instead of the dq. That's now going to become negative t, and now I have over RC. The integral of dt is just t. I already had an RC in the bottom, and the negative, like I said, came from the substitution. So I don't know why I switched to writing in green there, but I did. So we're going to go back to our red for a little bit. I'm going to go ahead and evaluate this, and of course, the natural log of CE minus Q of t, close the natural log, minus the ln of CE is the same thing as the ln of those two divided. So I'm going to write CE minus Q, and that's technically Q of t. So I'll put it in there this time. I might not write it anymore though. And that will be over just plain CE. That's the left-hand side. And that's equal to negative t over RC. And I'm even going to define a quantity tau called the time constant, which is just RC. And you'll see there's an extra credit problem on this week's module to prove that ohms times coulomb, or excuse me, ohms times farads gives you seconds. Okay. So now what I'm going to do is I'm going to raise e to the left-hand side's power. And I'm going to raise e to the right-hand side's power, and I'm going to set them equal to each other. And since I used e instead of 10, basically I'll just get the argument of the natural log. If I use the 10, I have to deal with the natural log of 10 as well. But if you use the same base, this comes off quite nicely. So now I have CE minus Q of t over CE is equal to e to the negative t over tau. That can actually be called, let's say, multiply both sides by CE, and we get CE minus Q of t is equal to CE e to the negative t over tau. Now I'm going to solve for Q of t. So I get Q of t is equal to C times E times 1 minus e to the negative t over tau. So this is the part that you're supposed to take home from all this. It would be wonderful if you could do this derivation yourself, but you don't need to. Okay, this is me showing it to you so you now know under what circumstances you're allowed to use this equations. For instance, I've told you that R is the total resistance. It's the resistance of the internal resistance of the battery plus the resistance of the wire plus the resistance of any resistor you put in there. Okay. It started off with the capacitor being not charged and the switch being open. And you then close the switch and got this Q as a function of T. So in all situations like this, this equation works. And the way this equation graphs is something like this. If I actually made a graph, say, of Q versus T, then what you'd see at T equals 0, that's e to the negative 0, and anything other than 0 raised to the 0 is 1. So that's 1 minus 1. So it's literally going to start at 0 here. And then it's going to asymptotically approach this value of C times E. And it's actually going to approach it like this. And in fact, at 1 RC, which is also 1 tau, if you go up here, this will be 0.63 times CE. That's a 6 and a 3. It turns out if you take e to the negative 1, that actually, e is 2.71828 roughly. So 1 over that gives you about 0.376, I think. So 0.37 from 100 is about 0.63. And that's basically where that 0.63 came from. Now, remember, from C equals Q over V, that means V equals Q over C. So V of T is just equal to Q over C. And both, by the way, both of these are the charge and the voltage across the capacitor. So with this in mind, you get a similar equation. It's just E times 1 minus e to the negative T over tau. So that's another equation you're just allowed to use, and you just know the circumstances. You're not required to do this integral and all that stuff and this, solve this differential equation. So you can tell V of T is going to look like the same thing, except this is just going to be E here, and this is just going to be 0.63 E here as well. And the graph will look exactly the same. Okay. Now, the other part is I've asked you to solve for Q of T across the capacitor, V of T across the capacitor. That's why I subscripted it C up there at the top. I didn't do that down here. It doesn't matter. And then I also asked you for the current going through the wire, and that's I as a function of T. And of course, we already defined I to be dq dt. So I is dq dt. So all I got to do is take a derivative of the Q of T. Now, you can distribute that CE and you'll get CE minus CE times e to the negative T. So that's going to have a negative CE out in front. The derivative of the CE term is just 0. So I'm now left with taking the derivative of e to the negative T over tau. And of course, remember, tau is RC. So the derivative of e to the negative T is just e to the negative T over tau like it was. But now you got to take the derivative using the chain rule, the derivative of negative T over tau. And that, of course, is negative 1 over RC. Or excuse me. Yeah, negative 1 over RC. So you can now see that, actually, I'll do it like this. You can now see that I of T is actually going to be equal to, notice the two negatives cancel out. The RC in the bottom cancels out with the C in the CE up top. So I'm going to get basically E over R, which is completely consistent with Ohm's law, because Ohm's law says current is equal to voltage divided by resistance. So it's E over R times e to the negative T over tau. And that is our expression. Okay, so those are the three equations you can use for charging a capacitor. They can do, you'll see some of the questions they give you in the actual textbook about this. These are really plug and chug problems where they'll say, okay, a resistance is 3 mega ohms and a capacitance is 4 microfarads. At what time will the charge be, let's say, 90% of C times E? So what you're going to do is you're going to replace the Q of T with 0.9 times CE and then solve that for T. So you got to, brush up on how to solve for exponents. Obviously, remember, if you take the logarithm of something raised to a power, that power comes out in front of the logarithm and you're left with just the logarithm of the base. So if you choose wisely on your logarithm, so for instance, if the base of the thing raised to a power, if that base was 10, you want to use log because that's base 10. If that number was 5 to the x, you'd want to take log base 5 of 5 to the x. So you'd end up getting x times log base 5 of 5, which is just 1. Okay, so that's the neat trick on that. They can also do stuff like they'll tell you the voltage in a certain RC circuit increased by an amount of 63% of or to an amount 63% of, and they'll give you some voltage. Okay, or they'll just say some voltage, which actually turns out to be, say, 63% of C times E. And then they'll say, what is the resistance of that circuit? And they'll give you the capacitance. Well, what they're telling you by giving you the 63% mark is they're telling you what RC is, because RC is the time elapsed for it to get to 63% of its max value, which is CE. So they'll do stuff like that, but it's all really straightforward sort of plug and chug stuff. That's the main thing. Let me see if I can find one to give you. I think I have enough time to do that and still get to the ammeter and stuff like that. So your book does an example, 2610. That says the capacitance in the circuit of figure 26.16a, which I think is pretty much the same circuit we just studied. Let me see. Yes. It's the same circuit we just studied. And now I don't know what's going on, but okay. They're going to say basically that same setup, but we're going to have a circuit going down to a battery. And then that's going down to a switch. And then that's going up to a capacitor. And then that's going up to a resistor. But of course, that resistance is supposed to represent all of the R's. They're saying C is equal to 0.30 microfarads. And they're saying R is 20 kiloohms. And they're saying this E is 12 volts. Okay. And they want to determine the time constant. So A, tau equals question mark. See, a lot of this is just learning the symbols and what they call it. So A equals a time constant. B, the maximum charge the capacitor could acquire. Well, B means basically Q, or let's write it this way. The limit of Q of T as T approaches infinity is the question mark. So they're literally asking the maximum charge the capacitor could acquire. Well, that's really, you saw it sort of an asymptotic function. It's asymptotically trying to approach the value CE, right? So that's what they're asking for there. Part C, they're asking for the time it takes for the change to reach 99% of the value. So C, T at Q equals 0.99 of C times E. Okay, so that T is equal to question mark. And then part D, they're asking the current I when the charge Q on the capacitor is half its maximum value. So I at T such that they're saying they're wanting to know the current I when the charge Q on the capacitor is half its value. So we're going to say Q of T is equal to 1/2 CE. So in other words, they're asking you to solve for the time that TE, or that the charge is 1/2 its value, and then evaluate I at that time. E, they're asking for the maximum current in the circuit. I max equals question mark. And then finally, F, they're asking for the charge on capacitor when the current is 0.2 of its maximum value. So F, they want to know Q at T when I of T equals 0.2 of its maximum, 0.20 times I max. Okay, so that's what they're asking. Now we know what our equations are, so we're pretty golden on that, having just derived them. But that's what you're supposed to use. You're not supposed to go through the whole derivation again. So what we're supposed to use is, first we're going to find tau. So here's part A. Tau is equal to just R times C. And R is, of course, 20 kilo ohms. And C is 0.30, which is 30 over 100. That comes in handy. 30 over 100 microfarads. Now a micro times a kilo is 10 to the 3, a micro is 10 to the -6. So that's a milli. So if I multiply 20 times 0.3, I'm basically, the easiest way is just divide 20 by 10, and that'll be 2, and then multiply that by 3, it'll be 6. So this is in fact 6.0 milliseconds. So that's your time constant. Part B, they want to know, okay, what is Q as that'll reach at a maximum. We know that Q is equal to CE times 1 minus E to the -T over RC, where I replaced the tau with RC for that. Now what we see as T approaches infinity, E to the -T goes to 0. So you can see it's just going to be C times E. So the limit of Q of T as T approaches infinity is in fact just C times E, which we can say C times E would be 12 volts times 0.3 microfarads. 12 times 0.3 is 3.6. So I'm going to say, whoa, why did it do that again? I'm going to say 3.6 microcoulombs. Okay, all I did was I took the C, which was 0.3 microfarads, multiplied it by the 12 volts, left the micro on there, and 12 times 0.3 is 3.6. So that's how I got that one. Any questions on that part? So you can see this stuff really is fairly easy. In part C, they want to know the time at which you reach 99%. So what we're going to do is we're going to say 0.99 CE is equal to CE times 1 minus E to the -T over tau. Obviously, these CEs cancel out. And basically, I get 1 minus 0.99 is equal to E to the -T over tau. That means 0.01 is equal to E to the -T over tau. Taking the ln of both sides, I get ln of 0.01 is equal to -T over tau. So T is going to be equal to the negative of tau times the ln of 0.01. Well, if I take the ln of 0.01, first I got to find the ln button. There it is. Ln button 0.01. That gives me negative 4.6051. That's what the ln is, times negative. And then of course, we found that the tau was 6.0 milliseconds, like that. So if I multiply that by 6, I now get a positive 27.6, and the units come out in milliseconds. So T 99% is actually equal to 27.6 milliseconds, which you can also interpret as basically 4.61 taus. Okay, so after 4.61 taus, we're actually up to 99%. So you can see really it doesn't take too terribly long to get to full charge. Part D, they want to know the current at the same time that Q of T is 1/2 CE. So all we have to do with that is say 1/2 CE is equal to CE times 1 minus e to the negative t over tau. Again, you're going to get 0.50. That's what happens when you subtract 0.5 from 10. Notice the CE's canceled out again. And that's going to be the ln of that. So let me make it a little clearer for us. So the ln of 0.50 is going to be equal to negative t over tau. So t is just going to be equal to, I take the ln again of 0.5. That turns out to be 0.693, negative technically. So it's negative 0.693, 1 carrying an extra digit, times another negative. So that makes that positive. Oh, excuse me. Let me not do it this way. That's going to make the algebra look confusing. So I'm going to say t is equal to negative 0.693 dang it, times tau. Well, that's times what we determined was 6.0 milliseconds. So that gives me 4.158 milliseconds. Okay, now I need to know I at that time. So I at 4.158 milliseconds. And by the way, I really only had 2 sig figs, so these are extras, the 5 and the 8 are. So I at that will be equal to, remember our I equation was basically just CE times e to the negative t. I think that's what I got. Yeah, no, E over R times e to the negative t. So 12 volts over 20 kiloohms. You can't actually use that. That's just going to make a milli. So a volt divided by a kilo is going to make a milli. So this will come out in milliamps. And then times e to the negative, basically 0.6931 tau over tau. You don't even have to plug the tau in there. And that's going to give you e to the negative 0.6931. So that essentially is exactly 0.5, which we should have known that because that's what the ln of e, or what e to the negative 2 is. So if we get that, now we just multiply that by 12 divided by 20. And that gives us 0.6 milliamps times 0.5. And that gives me 0.30 milliamps. So that's the current at that time. Okay, and assuming I didn't make any careless mistakes, but it looks like it went okay. E, they're wanting I max, and of course, E, whoa. Part E, I max is just what happens when E is raised to the 0 power, because that's the biggest it'll be. From there on out, the E raised to a negative power is making the I smaller. So it's just the 12 volts divided by 20 kiloohms, which is in fact equal to 0.30 milliamps. Which is the same we had there before. And finally, F, they want to know F, which is the charge when T equals, or when at the same time that I is equal to 0.2. So I equals 0.2 means 0.2 times E over R is equal to E over R times e to the negative t over tau. That's our expression. Again, the e over r's cancel out, and we end up taking the natural log, and you get basically natural log 0.20 is equal to negative t over tau. So t is in fact going to be equal to the tau, which we said was 6 milliseconds. So 6.0 times, and we're actually going to take the negative of the ln, because you see the negatives that are going to come in there. So I'm going to take the natural log of 0.2, and I get 9.66 seconds. And now what we want to know is find out what the charge is at that time. So Q at 9.66 seconds. As we can tell, it gets to essentially 99% after 4.61 taus. In this case, we're talking about 9 point, or excuse me, let's see what ln of 2 was. 0.693, or excuse me, ln of 0.2 doofus. We're talking about 1.60 time constants. So basically, we're going to say e to the negative, or e to the negative 9.66. So e to the negative 9.66. And now I'm going to divide that by the time constant, which was 6 e to the negative 6. Or excuse me, 6e to the negative 3. And that's going to give me that gave me 6.1 times 10 to the negative 700. Whoa. Something happened there. Very small. Okay. So let me reread the F question again. F was the charge Q on the capacitor when the current is 0.2 of its maximum value. Okay, I set the current to 0.2. The current was E over R times e to the negative e to the negative t over tau. So I got ln t equals negative t over tau. So ln of 0.2 was 1.609. So that was a ln times 6e to the negative 3. That gives me 9.66. Oh, that's why. 9.66 times 10 to the negative third. I forgot the milliseconds. So that's what happened there. So I can fix it right here. Q of 9.66 times 10 to the negative third seconds is going to be, obviously you're going to take 1 minus that quantity, that e to that quantity. So that's 1.609 tau. So it would be, we had Q was CE, so that's 0.3 microfarads times 12 volts times E, or excuse me, times 1 times 1 minus E to the 1.609 negative. That 1.609 is just basically 1.609 times tau, but then divided by tau. So I'm going to do 1 minus E to the negative 1.609. That gives me 0.799. And then 0.799 times 0.3 times 12, that was 3.6. That gives me 2.8 microfarads. So the answer is Q equals 2.88 microfarads. And that's actually the final answer, even though I wrote it in a weird order because I ran out of space. Could have.
Shouldn't Q be in coulombs, not farads?
Yeah, thank you.
And
Go for it.
yeah, I got a different answer.
Yeah, different answer. Yours might be
Yeah.
right. That
So
was
I just,
questionable stuff.
what I did was I of t is equal to 0.2 amps, or is it milliamps?
No, it can't be 0.2 amps. It's got to be 0.2 of the maximum, and the maximum is the E over R.
Okay, that's all right. So the maximum, shouldn't the 12 volts divided by 20 kilo ohms, isn't that 0.6 milliamps?
Yes, 12 divided by 20. I think it comes up with 0.6. Yeah, that is 0.6, and that is milli. Oh, how did I get 0.3?
Okay, so
yeah,
so
I wrote
F
0.3.
is Q when amperage is equal to 0.2 milliamps.
Yes.
All right, so could we, instead of solving for t, just solve for e to the negative t over tau, because e to the negative t over tau are in both equations?
Yes. Yeah, you should be able to do that. Now, like I said, there might be some arithmetic mistakes and all sorts of stuff on there. Let me see if I got another room. See, I don't really have room for another page. But let's go to the other. Well, do y'all understand what we did there? We were asked in part F to find the Q at time t, where time t gives you a current equal to 0.20 times E over R. So that 0.2 E over R equals E over R times E to the negative t over tau. When you go to solve that, the E over R cancels out, and you end up taking the ln of both sides, which is the ln of 0.2 is equal to negative t over tau. So you basically get t is equal to negative tau times ln 0.2. Well, ln of 0.2 comes out to be a negative 0.6093 or something like that. And then you're going to multiply that, of course, by the 6.0 milliseconds. And that's where you're going to get what the ultimate time is. That time you then plug back into the Q equation, which is what I was attempting to do on that last line. So as long as you know that's the process, it's okay if I got the wrong answer. Obviously, it's not not okay on a test, but the good news is we're doing mostly multiple choice questions. So if the answer is not there, from a weird mathematical mistake standpoint, you won't find that as an extra choice. But if you make a common assumption that's wrong or make some physical mistake that students make normally, you will find an answer there that matches. So you're sort of protected against careless math errors. A careless math error is not going to play out that way. In other words, you're not going to find an answer for it. So be very cautious if you get a result on a test that doesn't match any of your answers. Chances are you made some kind of careless mathematical or algebraic mistake.
Yeah, for part F, I got 2.4 microcoulombs for, but what I did was I just solved for e to the negative t over tau instead of solving for time and then plugging all that in. E to the negative t over tau should be 1/3. So 1 minus 1/3, you just get 2/3 of CE.
Gotcha.
I don't know if you're getting that as well,
good,
if you want to go through it again.
Yeah, I'll go ahead and go through it again. You probably did everything right. So let's see. You did say 0.20 times E over R. Actually, let's reread the question again. Part F was, I want the current, which we know is an equation E over R, e to the negative t over tau. Okay, we want the current to be 0.2 of its maximum. So that's E over R. That's equal.
So what's the charge on the plates when the current is 0.2 milliamps?
Exactly.
Right.
But we first got to figure out the time. So yeah, you're right. We do want Q. We want Q when I equals 0.2 I max. That's another way of writing it. So this is E over R, e to the negative t over tau. Again, our E over R cancels out. We get the natural log. Whoa.
I thought it was just 0.2 is equal to E over R times e to the negative t over tau.
No, it's got to be this.
Equation of I of t is E over R e to the negative t over tau, right?
Right.
And I is 0.2 milliamps.
No, it's not.
So we already know what I is.
No, it's not 0.2 milliamps. The I was 0.2 of its maximum value.
0.2 its max. Okay, I got.
Yeah, and its maximum
then I was
value
using the wrong
really
thing.
Yeah, your maximum value is really E over R. And it looked like from what you told me earlier that I did calculate E over R incorrectly. I think I got 0.3 instead of 0.6 for some ungodly reason. So I corrected that in the notes. But at this point, we're just going to take the natural log of 0.20 and multiply that by tau, and we'll get and multiply that by negative t, by negative tau, and that should give us t. So in fact, t is equal to, do the math again. That's 1.609 times tau, which is a unit that's really convenient to work in anyways, but I'm going to go ahead and put that in seconds too. So that times R, which was R, which was 12 microfarads, or 30 microfarads. E to the negative 6 times C, which was, R was 20 kiloohms. 30 times 10 to the negative 6 micro times 20 e to the third. That gives me positive 9.9566 seconds. But that 1.609 is fine to use as well. So now I got to figure out what the Q is at that time. Well, Q of 1.609 tau is a lot easier to calculate Q, of course, is C times E times 1 minus E to the negative 1.609 tau over tau. So now you can see those taus cancel out. That's why it's such a convenient unit. Now, if you raise E to the negative 1.609 power,
You should just get 0.2, right?
exactly.
So
You get
so we
0.2.
could have just plugged the E to the negative T over tau equals 0.2 into the Q equation, right?
Exactly, because it
And then
automatically
we just go CE times 0.8.
And that's the physics. That's the actual concept that they're trying to get you to see. CE times 0.80. And of course, that's going to be basically 0.8 times C times E. Well, the C was 30 microfarads times the E, which was 12 volts. So 30 times 12 is 360. And that's 360 micro coulombs. And then times 0.8. That's 288 microcoulombs, which is entirely different from what I
It's
got.
2.88.
2.88. Thank you. So let's check. Okay. So that's gonna give me 0.2. That's 0.8. So 0.8 times 30 e to the negative 6 times 1, 2. No, I have to get 288 microcoulombs, not 2.88 microcoulombs. I don't know how you
If you just do 0.8 times 0.3 times 12, you get 2.88. And since we know 0.3 times 10 to the negative 6 is what
Okay.
the coulombs is, then we could just transfer
that's the
the
problem.
10 to the
Yeah, you've got it now. So yes, I was using 30 microcoulombs, not 0.30. So yeah, you're exactly right. I don't know why I was using 30 microcoulombs, but yeah, that would bring it off by a factor of 100. And of course, that makes it 2.88 microcoulombs. So yeah, we agree on that. Sorry about that. For some reason, like I said, I started doing that. Of course, time's up. You guys are of course free to go. I'm probably going to go ahead and finish out. No, I'll just leave it all. There's a video for completing or creating an ammeter out of a galvanometer. There's a video for completing creating a voltmeter out of a galvanometer. And there's a video for discharging a capacitor as well. So I've actually covered the remaining stuff in the chapter anyways. If you have any problem with those, let me know. But the homework's still available. You got another class meeting for me. We're not tested on this so far. We were tested on 21, 22, and then 23, 24. And the next test is 25 and 26. And I'm probably going to open that this week. But I'm also probably going to soon thereafter open up the practice midterm 2 versions, and the practice and the ultimately the midterm will come on the 20th of October. So if you have any questions, stick around. I'm going to wait for the last person to leave, but everybody's free to go. Thanks for coming, everybody, and enjoy your night off of lab.
Can you actually post the last video from Thursday on YouTube?
Yes, I think I just discovered that I hadn't done that. I was doing the one from the previous week because I had some problems. So the last video was on 9/22. Am I right? That had been 5
that's
days
correct.
ago. Yeah, 27, 26, 25, 24, 23, 22. Yeah, and part of the reason is I put that in the 240 in a name with a 241 name instead of 242. So that's what happened there. So yeah, I'll go ahead and post that immediately. And then you'll post this other one right after that one's done. Okay.
Okay, thank you.
Thank you. And that looks like it. Stop sharing. And the meeting for all.